So welcome to this lecture on VHDL in the course Digital System Design with PLDs and FPGAs. In the last lecture we have looked at basically how to write packages, to write components in a package and put it in a library and instantiate it in some top level entity. Also we have looked at the configuration specification and configuration declaration, which talks essentially about how to say, like you are instantiating some components from a library. So the configuration specification bind this instantiation to a specific library, specific package, specific entity and specific architecture. That is a basic idea. And configuration declaration does this thing in a separate design unit. Also it has an additional function. Suppose the top level entity has multiple architectures, it tells which architecture to be used for that configuration specified. So depending on how you write configuration, even the top level entity can have multiple architectures. That is the basic idea, because when we at the beginning of the lecture we have discussed that the VHDL can have multiple architectures, but we did not say how the tools are going to infer which architecture you require. Okay. So this can happen in two scenarios. One scenario is that you have one entity and multiple architecture, and you want to use at the time of synthesizing or simulating or implementing, whatever may be the case, that a particular architecture. Suppose you have an entity with 3 architectures and you are just going to use that entity alone, that component alone, and you want to say out of the 3 which architecture to be used for the current compilation. Okay. So that is done by the configuration declaration. In addition, suppose in your entity you are instantiating components from library, and you can specifically say a particular component should come from a particular library, otherwise you will be at the mercy of the tool, because there could be similarly named components in various packages and various libraries, and if you just say some library name and use that library dot package and various, maybe you will write some 5 use clauses. So the tool will pick whichever comes first. To suppose you have used a component called counter, the tool is going to look at the first package, second package and so on. Wherever it finds a name which is matching the instantiation, and the arguments of like various ports, you have the you have the data type, and if the data type matches it will pick up that particular component. Probably that is not the one you want, then in that case you can very specifically say a particular component instantiation. You can go to the level of specifying a particular label. Suppose you have used XOR gate 5 times, like suppose the labels were X1, X2, X3, X4, X5, these component instantiation labels, and you can say for X1 it has to come from a particular package, and for X2 maybe from another package and so on. So it can be very specific, very detailed. So that is what we have seen in the last lecture. So let us quickly look at the slides of the last lecture for a revision. So we have taken an example of a double synchronizer as a top level entity and a flip flop as a component, and we have seen that in the normal course you will write the code for the flip flop. So the library, entity and architecture, and in the same file or in the same project you will have the double synchronizer circuit, the top level entity, which has the input and the clock and the output, and you declare the component which is this particular data flip flop, declare the signal to interconnect because you will have to declare this internal signal, instantiate it twice and connect all the signals, and that is what we have done. Declare the component, declare the signal. The first flip flop is instantiated with appropriate mapping, second one, that's it. But when you write okay, this is a bit about the package and library. The hierarchy is that library, multiple libraries, within each library you can have multiple packages, and within a package you can have components, functions, procedures and data types. And there are predefined library, one is STD which contains these two packages, standard package and text.io package. This is what which contains the bit, binary, the real, all those definitions and all the operators related to it. And the text.io is used for file operation which can be used in test benches, and the work library is the one which your current design, whatever you write, is compiled into the work library. And normally it is understood that without these two no tool can work, so you don't kind of explicitly declare these like libraries, std, work is not required, it is implicit, it is understood. Similarly the essential package in this standard library is standard, so you don't have to say use std.standard.all. This is implicit, this is assumed it is there, and but if you have to use a text.io in the std library, that is not implicitly declared because it is not used often, it is used only in the test benches, and so when you want to use it you have to say use std.text.io.all, and this is how we write the package. So the top you write a package header, follow that with the entity and architecture, and we are calling our component the same component DFF. So at the bottom you have a library, entity and architecture of D flip flop, and at the top you have a package header, package some name is N package. Within that you write the component of this DFF exactly same as the component declaration in the top level entity, which is nothing but this entity, whatever is inside the entity is repeated there, and that's it. Once you do that this particular component is the package definition is over, and this can be put in a particular library, and that is tool specific, vendor specific, how to compile a package into a library. You have to refer to the manual or the user guide of the tools you use, but when we go for a demo we can definitely see that at least the package the tool we are going to use, how to use that, within that tool we will see. So how to use this, the fact that you have put a component in a package and compile into a library, but we have to see how it is to be used in a top level entity, in our case this double synchronizer. So first thing is to note that we have put that package in a particular library, so you have to add the library clause, library xylib, that is where we have assumed we put this xy package, and you have to say use xylib.xy package.all. Then comes the entity, but in the architecture declaration region we don't have the component declaration because now that is part of the package or part of the component which is in the library. So we don't have that, we just declare the internal signal which is required, and then we instantiate as previously this particular component. That's all what is required, and as I said you can have multiple component in a package, it doesn't matter. Suppose you have 10 components, you can include the component declarations, all the component declarations within the package body, and follow it up with the entity and architecture of all the components. Okay, suppose you have 10 components, write the entity and architecture of the first component followed with the second component and so on. You can write that in a single file, compile it into library. That is simple as it is, and definitely when you instantiate you can use positional association or named association. This is anytime better than this particular thing where you have to keep we have to remember the order of the formal parameters, which is sometimes difficult to know. And moreover, when you write a component, one would like it to be generic, because if you have a counter then you shouldn't be worried about 8-bit counter, 16-bit counter and so on. You should have a counter which is generic in size, and when you instantiate it you should be able to specify the size. We have seen that, and how we do is that instead of hard coding the size, we define a constant called generic is nothing but a constant. Say here it is called size, and we say size is 4, we say size minus 1 down to 0. So the syntax is that in the entity declaration you include generic and open the parenthesis, and within that you can write any number of generic depending on the requirement. Say here we require only a size, but in the case of a FIFO we have discussed, maybe you have a data width and the size of the FIFO in terms of locations and so on. So here size is declared as an integer with a default value of 4. This is the default value. When you instantiate, if you don't specify anything, then it is treated as 4. Okay. So and definitely for a 4-bit vector we have 3 down to 0, so we say size minus 1 down to 0, and we have a signal. So wherever required the size is required, then you say size minus 1 down to 0, then follow it up with the architecture, and at the top you have a component declaration which is nothing but similar to the entity. So all these appears at the component side, then you can put it into a library, but then we have to see how to use that, okay, how to specify the size we require when you instantiate it. So that is what is shown here. In the normal case, if you say count, that is the counter we have put, port map and the input signal, output signal, the width will be 4, but you want a specific width. So like ports are mapped, we have to say generics are mapped. So the count, generic map and 8, and there is only one generic here, so that gets the value 8. So everything here is 7 down to 0 now. Okay, so you get an 8-bit counter, and if there are multiple generics then you have to say comma, like here you can say comma 16 and so on, and this is nothing but positional association. You can have a kind of named association which say size, that is what it say here, size, and with the forward arrow 8 you can say. Then if there are multiple generic then you put a comma and the next one and so on. Okay, and this is the normal port map. So you can have any number of parameters, and we have seen an example of a NAND gate with propagation delay TPLH and TPHL defined, and we have seen that the behavior is specified like O1 gets I1 NAND 2 after TPLH plus TPHL by 2. Okay, and we have also seen that when you instantiate a particular component in a top level entity, the top level entity's generic can be passed down to the component which is instantiated. Okay, example we have treated was a counter which is a generic counter which is instantiated in a generic timer. So naturally the width of the timer will be width of the counter. So when you instantiate the counter in the top level entity of the timer, top level architecture of the timer, then instead of hard coding it we say the generic of the timer T width. So when that is ultimately specified, it is going to be instantiated or specified, then like the timer can be instantiated in a CPU, then that will be specified at that time and that will be passed down to the counter. So that is the generic in hierarchy, and this is a configuration specification which tells how to bind the instantiated components to entity architecture pair, and this is specified in the architecture declaration region. Configuration declaration has the two purposes. One is the same purpose, bind the components to a particular library. Also it binds a top level entity of this particular top level design to a particular architecture it has, okay. And this is a separate unit, this is hierarchical, okay. We will see what is the meaning of that, and we have seen an example, a full adder with 2 XOR gates, 3 AND gates and 2 OR gates. So the component declaration is XOR, and OR, and we have in the architecture statement region we have instantiated this, but in the declaration region you can say for x1 x2 that those are the labels of XOR2 instantiation, that it comes from use entity library dot package. Here there is no package, but because it is in the work library, so the entity and the architecture, okay. For A3, that means in the AND gate A3 alone, use entity, this library, this entity, this architecture, and whatever the formal ports which is in the library is mapped to something called A1, just a name change in case you have used a different name here, okay. We have not used, we have used a positional association, so probably this does not matter, but suppose you have said instead of HSB, suppose here we write say for A3 we say instead of saying HSB map to S4, suppose you had said kind of A1 map to S4, then this could be done to change it. And there are two special syntax for all OR2, that means for all the instantiation of OR2 use a particular entity architecture pair, and you say for others, that means here you see AND gate instantiation for particular A3 we have used a particular component from a library. For all others, that means A1 and A2 use something from elsewhere, that is the way it is specified. And when it comes to configuration declaration, for a symbol binding of the entity, top level entity to architecture, you write a configuration name of the entity, you say for a particular architecture name N4, that means this entity is mapped to this particular thing, that is all. But you want to specify the component binding, that can be done inside. So you say for A1, A2, A3 use a particular AND gate and say N4, for others OR2 N4, that means we are not specifying anything. For all XOR2 use configuration work.xorcon, that means the XOR2 has a configuration as part of its entity architecture which say that which are the where this particular thing should come from and which is the architecture to use all that. So that shows the hierarchy of the configuration. So I think this is what we have started briefly in the last classes. So there are different packages, and different packages as different operators, functions, and it can be little confusing at the beginning which particular operator to use, which particular function to use, and so on. So we will look at, and it is very difficult, maybe it is not given in a textbook sometime, and one way to know this particular operator's definition is by looking into the libraries, okay. That would mean that you go through the source code of the library. Okay, that is a very cumbersome thing because you have to open the source of the library in VHDL or Verilog, go through all the code, and in the process you make some changes to it, and then if you compile it for some tool, simulator tool, then it can give errors and all that. So I am giving you a brief about the various packages, various operators and functions. So the primary package we have come across other than the standard package is the standard logic 1164, where this standard U logic is defined with all the 9 values. We have seen that. Okay, and a standard logic is nothing but a standard U logic, but it is going through a resolution function in the case of multiple drivers, and we have a standard logic vector, standard U logic vector and standard logic vector, which is defined as an unconstrained array of standard U logic and standard logic respectively. So it can take any value of 2 raised to 32. Okay, and when we declare, we constrain it by specifying the size, and standard logic 1164 contains only the logical operators for this particular standard U logic, standard U logic vector and standard logic vector. So if you want to do some arithmetic with it, then we need to use a different package. This contains only the logical operators. So please keep that in mind. So the next thing we have already seen in some example, which is the package standard logic unsigned. This is also the IEEE package. So it is written IEEE dot standard logic unsigned. It has standard logic and standard logic vector as a data type. The operators like plus, minus, multiplication, division is overloaded for it. Also it has relational operators, all greater than, equal to, not equal to, less than or equal to, greater than or equal to, all that is there. So you can, the moment you say use IEEE standard logic unsigned, you can use all these. In addition, it has shift operators which is called SHR, which is shift right, and SHL, which is shift left. Okay, mind you, this is all logical shift, there is no arithmetic shift which is offered in this particular library. So if you are working with 2's complement, maybe it is little difficult. Either you will not be able to use this particular operator, you may have to write code for arithmetic shift. Okay, and as I said, the digital design, when you design through the VHDL, it enforces strict type checking. So suppose you have a standard logic vector which has to be converted to integer, then you have to specifically convert it to integer. It will not be, you cannot assign a standard logic vector to an integer. Maybe it is 8-bit, but you know that the 8-bit goes from 0 to 255 for unsigned, but that, like, you cannot assign that to an integer unless you convert standard logic vector to an integer. So this particular function convert this standard logic vector to integer. You can say conf underscore integer, open the bracket, and whichever is your standard logic vector, the object you can put here and it will return an integer. That is how this is this particular function to be used. And there is a synopsis specified library which is called std underscore logic underscore arith. Okay, now that does not use a standard logic vector as a base vector type. It has 2 arrays of standard logic which is unconstrained. One is called unsigned, other is called signed. As the name suggests, that can be used for arithmetic. You can have unsigned addition and signed addition. It is exactly similar to standard logic vector, but then the name is unsigned and the name is signed here. So you have this package has all the operators overloaded for unsigned and signed. So you have all the arithmetic operators, all the relational operators. Like in the previous case, you have, like standard logic unsigned, you have SHR and SHL, but if the type you are using is unsigned, then it is a logical shift. If it is a signed data type you are using, then this will be an arithmetic shift automatically. So you do not have to worry. So if you play with the 2's complement number, then this can be very useful, because you do some kind of computation with the sign extension, then you have to shift it properly with the sign bit, otherwise the value will not be correct, the result will not be correct. So this is taken care of in this SHR and SHL, the provided you use the proper data type signed. So it also has conversion function. So basically it has conversion function from standard logic vector, unsigned, signed and integer. So there are 4 conversion functions. So the convert integer will convert from all the other 3, like standard logic vector, signed and unsigned, to the integer. So you just open the bracket and write whatever. So that means this convert integer is overloaded 3 times in this case for standard logic vector, for unsigned and signed. Similarly you have convert unsigned, which will convert from standard logic vector, signed and integer. Convert signed, convert standard logic vector and all that, okay. So that means it means that it convert to standard logic vector, convert to integer from these 3 types. Whatever is not mentioned here is the from kind of data type. Now if you want to use this libraries, synopsis libraries, you say library IEEE, use IEEE standard logic 1164, because the standard logic base type itself is defined here. Then you say standard logic arith, wherein you can use kind of all the arithmetic relation shift and logical operators and functions, and you say at the end IEEE standard logic unsigned, because the shift operators unsigned has there are arithmetic and shift and all that operators here, and mind you this is put below this so that main operators are from the arith. So these are the recommendation for all the design. You have to use standard logic arith, and unsigned you can use it for counters and test benches, and don't use a package. There is a package called std logic signed, don't use it. Now like there is a package from IEEE standard like in place of the synopsis packages. So these 2 are synopsis packages, arith and arith is a synopsis package. So there is another similar package from the IEEE, so that is called numeric _ std, or we call numeric standard. Similar to arith, you have unsigned and signed specify as array of standard logic, and you have arithmetic operators. Now you not only you have plus, minus, multiply and division, you have absolute, rem and mode you have. In the numeric standard you have relational operators, you have logical operators, you have shift operations, you have shift left, shift right, rotate left, rotate right, SLL, SRL, which is nothing but this, ROL, ROR, which is nothing but this. So exactly same, and you have conversion function to integer to unsigned, signed from like if you take 2 integer, it is from unsigned or signed or standard logic vector, and similarly others. And how to use this particular package. So you say library IEEE, library use IEEE.standardlogic1164.all, that is required because standard logic is defined there, and use IEEE.numeric standard.all. Okay, so that is how the IEEE numeric standard library is used. In the earlier case we have seen that we have to use 1164 unsigned and arith, but here is only numeric standard need to be used. So that is the various libraries, various packages, operators and functions. Now when it comes to type conversion, many a times you have to do, because we use different libraries, and so you have to move between sometime standard logic vector to signed and unsigned and integer and so on. So there are 3 ways you can convert. So it is automatic between base type and subtype. Okay, so suppose you have a subtype, then you don't have to worry, you have defined a subtype of something, then you don't have to worry, you just assign it, will work. It is automatic, you don't have to do the type conversion. In some cases you have to use the explicit conversion function like to integer, convert integer and so on. Maybe say you have to convert from standard logic vector to an integer. So you can use either of these functions, and you know that the signed, unsigned and standard logic vector all are the unconstrained array of standard logic. So essentially, though the name is different, the data type is same, it's only the name difference. So the VHDL allows you to do a typecasting as in C. So when you convert between these 3, between any 2 of them, then you can just use a typecasting. Say suppose you have a standard logic vector called SLVect and you want to assign this unsigned vector USG_vect to this. You don't have to call to standard logic vector or to standard logic or convert standard logic. Just say std logic vector open bracket and just write the USG vector, you get the standard logic vector. And similarly, suppose you have a USG unsigned vector and you want to assign a standard logic vector, you just say unsigned, then you give this standard logic vector as an argument, then unsigned vector will get it. And particularly suppose you want to use some numerical value for whatever purpose, and say you want to pass this as signed number, then you just say signed, in the code you give that numerical value of the standard logic vector, it will be automatically converted to the signed data type. Okay. So that is about do the type conversion between the various similar data types. Now you should be careful when we call a function, say suppose in some case we needed a standard logic vector to be converted to an integer. Okay. So we will call a function which convert the standard logic to an integer. Okay. And if you know that suppose you have a 4-bit binary number, to convert to an integer the algorithm is that just simple, you iterate through the binary number bitwise. Wherever there is 1, you say you have an accumulator, you say that accumulator is nothing but accumulator plus 2 raised to I is the current index of that bit position. Okay. So if you have 1010, so it is basically 2 raised to 8 2 raised to 3 plus 2 raised to 1, which is 10. Okay. So and that you go through an iteration, like for I in 0 to 3, then if I is 1, then some variable is variable plus 2 raised to I and so on. Okay. So that is how it is computed, but like you should not think that this is going to be synthesized into a hardware. Okay. The data type checking is enforced by the VHDL as a language. Okay. So the fact that we write some code to convert a data type, that should not be synthesized into a circuit. Okay. So basically that you should understand, and so there are attributes which say, like when you write a library function for this type conversion, there are some like attributes which is inserted so that the synthesis tool will not synthesize that part of the code, that you should understand. So that is what is written here, but having said that, sometime when you convert, suppose take an example of memory. Okay. And suppose you have a memory with 8-bit address. Okay. And so the number of locations are 256. It will be normally addressed from 0 to 255. Okay. Now like in VHDL code, you can specify an array of location indexed by the address. Okay. So you will have a memory array which goes from 0 to 255. So when you suppose you are reading a memory location, you would put the output of that particular memory location to a data bus, and you need to specify the array index. So to that extent we will kind of convert the address which is in standard logic vector to an integer and supply this as an index to the array. Okay. Now though the type conversion does not imply any hardware, but there is a hardware here which is hidden. That means you are converting an index which is in standard logic vector to an integer which is indexing an array. Okay. Then that represent an address decoder, because you know that in a memory a particular location is accessed by an address decoder. You specify the address, a particular decoder will go and select a particular location, and so that like implicitly sometime this the type conversion, not the type conversion alone, but the fact that that converted integer is indexed into an array can represent a address decoder. I maybe what I have written is a little kind of misleading. It is not the type conversion which implies an address decoder. The fact that that converted number is used as an index into array can mean that it is an address decoder. So that is what I want to convey. So I hope you are kind of clear about this particular type conversion. So let us see some examples of arithmetic. Okay, maybe some kind of at least at the start this will bring in clarity. Suppose you imagine there are A, B, these are the input kind of vectors, 8-bit vectors, which is defined as unsigned 7 down to 0. S is we are going to assign some output unsigned 7 down to 0. This is all these ABSs are 8-bit, and we have an 9-bit S which is called S9 which is unsigned 8 down to 0, and we also have an S7 which is unsigned 6 down to 0. Okay. Now very simple addition, suppose we are kind of doing an addition or you are implementing an adder, then the simple addition is that you say S get A plus B. Okay. Now A is 8-bit, B is 8-bit, and S is also 8-bit, and which normally in a digital course you would have learned that you add 2 8-bits and you end up with a 9-bit, but when you work with the operator you add A and B and you just end up with in kind of 8-bit result. The carry is ignored when it is synthesized or implemented. But in some case you like when we suppose you are doing a multiplication, we are trying to design a multiplier, then you know that in the multiplier algorithm you need to add the partial products and therein and then you have a shifting. So there if you add 2 8-bit that will result in a 9-bit and we require the 9-bit, okay. In that case maybe in a simple addition we may not require the carry bit, but there are cases where we require the carry bit. In such a case what we do is that they see how we can get that 9-bit. So S9 is a 9-bit vector which is assigned, then we append 0 at the as a most significant bit of A. So you say 0 concatenate with the A which is 8-bit plus 0 concatenate with B. So if there is a carry from the MSB which is 7 down 7 A7 or B7 position, then that goes to the 8th position and you get a 9-bit result, okay. Suppose you want to live with only the 8-bit result, then you can definitely say a 7-bit result, then you can say A6 down to 0 plus B6 down to 0. Suppose you want to you have a larger input and you have a smaller output, then you pick up the same size as the output, then you will get there is no issue because this is 7 down to 0 which is 8-bit, but S7 is only 7 bits wide, so you use A6 down to 0 plus B6 down to 0. And some cases you may need to supply a carry in, okay. Maybe you have split the adder for whatever reason into 2 stages, the carry out of the previous stage come as a carry in of the next stage. In such a case we do the opposite of appending 0 at the MSB position. What we do is that this is a 9-bit result and A and 1 at the least significant bit plus B and the carry input, okay. So you get the S9, okay, 9-bit result, but this part should not be part of the address part of the result, okay, because which say that suppose we are not interested in having the sum output, we want to push some carry if it is generated to the first stage. So here we have made it 1, so if the carry in is 0 then the carry out from the first stage is 0, but if it is 1 then 1 plus 1 is 0, the carry into the second stage is 1. So but this one output, the sum output itself at the least significant bit is not what we require, so we ignore it. So ultimately you just take the up to the first bit from the 8th bit and cast it to an 8-bit result, okay. That is how we use the carry in if required. So this shows how to use a carry out, this shows how to use the carry in with the standard operators, and we have used, so you do not have to write a ripple adder code or the carry lookup adder code. Normally you can stick with this plus, and in the case of FPGA there are dedicated resources to implement the plus, so which is very kind of high performance, area efficient and so on. We will see that when we go to the particular FPGA lectures, and that is about the arithmetic with kind of addition with the carry out, with carry in and so on. So now let us look at arithmetic with time. That time is specified as kind of integer units, so you say 1 nanosecond, 2 nanosecond, you do not say 1.5 nanosecond. So but when you do some, at least for simulation wise, when you do some calculation like you want to calculate the period and you want to multiply the period with something, then you may end up in a kind of real numbers. So it will be good if you can convert the time to a real number. So suppose here I am showing that we declare a variable which is named period, which is of type real, and now we say period get real, that is a typecasting, and time data which is in nanosecond, say 100 nanosecond, divide by 1 nanosecond. So we remove the unit and you get 100, and that is casted as a real, and then you get the period in real. Then you can multiply, divide, then you get the real number as a result. So that is how we do the arithmetic with time. So briefly we have looked at the packages, basically the IEEE standard logic 1164 package, standard logic unsigned which is IEEE library, a synopsis package called standard logic arith, how to use that, various arithmetic operators, relational operators, logical operators, shift operators and conversion function, and we have seen numeric standard how to use that. We also said the type conversion is not kind of doesn't represent a hardware, it is just for the language type checking, but when we in special cases when we convert and use it for indexing an array, it can represent some decoder, that shouldn't be forgotten. And ultimately we have seen some example of arithmetic like some similar size result as a input when you add, and when you have a carry input what to do when you have a carry output, how to get the result of the wider result with the carry out and so on. And we have ultimately seen the time, some computation using the time during simulation where we convert the time unit into the real number so that you can multiply, where you end up with the fractions, then that can be preserved if you convert to the real number. So let us talk about this particular topic, and which is called delay modeling, how the VHDL model the delay. We have already seen the syntax, we say that something get after 5 nanosecond, then there is a delay for that output to display or to come out with a 5 nanosecond delay. So there are two types of delay specified in the VHDL, one is called inertial delay and another is called transport delay. So basically inertial delay will model the delay through capacitive networks. You know that you have a line with capacitance, you apply some binary value, then that capacitor has to charge up to that particular value, and before that, before it getting fully charged, if the input applied is removed, then there won't be any effect. So that is what is inertial delay, and that works for the gates with threshold, because you have an inverter and you apply a 1 at the input of the inverter, then naturally there is a capacitance on the line and the input has to charge up, say previously it was 0, above the threshold for the output to start appearing. Okay. So there is, like at the input there is some certain pulse width, then only like a minimum pulse width, then only the input will go above the threshold and the output will appear. Okay. And also there is a propagation delay. So inertial delay has two parts, one is a minimum pulse width which is required for the output to come. Okay. Suppose once again, suppose you have a inverter with a 5 nanosecond delay, and if you apply a 1 nanosecond pulse at the input of the inverter, for sure you can be sure that it will not make any effect at the output, it will not appear at the output, because the propagation delay was 5 nanosecond and you apply a narrow pulse of 1 nanosecond, so it will not appear. Okay. But we are not in a position to say that you apply a 4.5 nanosecond pulse whether it will appear at the output. Okay. That we are not able to say. At the gate level we have no great way to predict this by simulation or anything like that, but if you consider the equivalent transistor layout and do, like suppose you have made an AND gate or an inverter using say take an inverter with a PMOS transistor and NMOS transistor, do the layout, do the place and route of a VLSI chip and do a SPICE simulation, then you will be able to see the exact effect. But when we model this at the gate level, we do not have such accuracies, okay. So it is at a very gross level we are going to model, and it has limitation. You should understand that there are certain limitation with regard to this kind of modeling, and that can be reflected. There will be side effect. If you are careful in simulation, you will see the effect of this in certain cases depending on particular model used to represent the delay in the VHDL output code, particularly for simulation, timing simulation and so on. So it has two parameters. One is the minimum pulse width required for the output to appear. Second is the propagation delay itself, okay. So we will see, so that is the inertial delay. So we will see the inertial delay and move on to the transport delay. So let us look at the inertial delay. The syntax for it is that, say, x gets a after 5 nanosecond, okay. That means the meaning of it is that between x and a there is a 5 nanosecond delay. Also it means that anything less than 5 nanosecond, anything less than 5 nanosecond, suppose you apply to a, will not appear at the x, okay, that is the meaning of it. But exactly same, if you say x is inertial a after 5 nanosecond, it is same as like a after 5 nanosecond, because the default delay is inertial. So whether you say a after 5 nanosecond or inertial a after 5 nanosecond does not matter, but in this case the minimum pulse width is 5 nanosecond. But suppose you have a case where the pulse width required for the output to appear is 3 nanosecond and the propagation delay is 5 nanosecond, which probably may not be true, like it may be very close to 5 nanosecond, but take this case, then you can specify, you can decouple the minimum pulse width and the propagation delay, and the syntax for that is you say reject 3 nanosecond, inertial a after 5 nanosecond, okay. So it means that anything below 3 nanosecond will be rejected and anything above 3 nanosecond will be delayed by 5 nanosecond. Also you can say that you get, say, 1 after 5 nanosecond, 0 after 8 nanosecond, 1 after 12 nanosecond. It means that you will get a signal for first 5 nanosecond 1, next 3 nanosecond, because here we are saying the real time, okay, real. So for first 5 nanosecond will be 1, next 3 nanosecond it will be 0, and the next 4 nanosecond it will be 1. So this is a very useful kind of syntax to generate some waveform, and particularly this is useful in test benches. So that is about the inertial delay. And transport delay is the delay through a transmission line, okay. Basically no pulse is rejected, you know, you have a long line of bus, okay, and you apply a pulse irrespective of the width of the pulse, it is going to go to the other end with a delay, okay, but it will not be rejected because the pulse width is some kind of less than something. And way to specify the transport delay is you say Z is transport a after 5 nanosecond, okay. You say instead of inertial you say transport a after 5 nanosecond, then you get the transport delay. So maybe I will show some examples, the waveform and some kind of cases where this delay modeling is used for verification, but just for today we will wind up at this part. We have told about delay modeling, which is inertial delay and transport delay. Inertial delay kind of model the delay through capacitive networks or delay of a gate with a threshold, which essentially means that you need some minimum pulse width at the input for the output to appear due to this threshold crossing and the propagation delay. And at the, as I said again, at the digital gate level we have kind of gross delay, we can't be accurate. But if you take a VLSI transistor level implementation, do the SPICE, you will know the exact delay. But this is very useful at least where such, like from the SPICE simulation, such delays are known, then we can, if knowing the device characteristics, you can model using this index reasonably correctly, because it allows you to specify the minimum pulse width and propagation delay. So we have seen the syntax for that. Default is inertial, so we have in the simple case when you say A after 5 nanosecond or inertial A after 5 nanosecond, the propagation delay and the minimum pulse width is same. When it is different, use a reject clause, and you can generate waveform by specifying the various values using this syntax. And the transport delay, model the delay through a transmission line wherein there is no reject, like there is no minimum pulse width requirement, and the syntax for is that Z, some output get transport A after 5 nanosecond. Okay, as I said in the next lecture we will see some kind of an example of this syntax with the waveforms, and we will also see maybe how to use this delay modeling to verify some timing of a flip flop. We will see that, and then we will go through some maybe the VHDL code examples in the next lecture, so that you're familiar, you get some good familiarity with the VHDL language. So I stop here, please revise and don't take it lightly just because it's a language, because it represents the hardware. You have to get into the habit of thinking hardware than just treat it as a language. So I wish you all the best and thank you.